Alright, so in this video I want to kind of give you some applications for matrices, because a lot of people, a lot of students look at matrices and they go, what? Like, what's the point of these things? But in terms of digital images, matrices are very, very important. You know, whenever you go to Google and you search for something and you go over to images and you look at a whole bunch of pictures, all of those things are digital images. And each digital image is just a collection of pixels. Now, a pixel is just a tiny picture element. Pixel is just short for picture element. They're little squares of color, okay? And a computer stores an image file as a matrix. So look at this picture of Felix the cat. It's a very, very simple digital image. And think of it broken up as tiny, tiny little squares, right? And this is a oversimplification just so that you can get the point of it. So if you look at the actual image on the left-hand side, you see two colors. The pixel is either black or it's white. So right next to it, if it's a white pixel, it's getting the number 1, and if it's a black pixel, it's getting the number 0. And so this is a very simple case of how a computer can store an image. Just a whole bunch of numbers. And then the computer would just read those numbers off as to what color it's supposed to correspond to. Okay, so like I said, that's an oversimplification, and that was just black and white. But really, pictures have a whole bunch of colors. So any image is actually composed of 3 matrices, one for each color channel. You have a red, a green, and a blue, which is why you often see RGB in terms of colors for monitors. Okay, so you have, say, a red color channel, plus a green color channel, and then plus a blue color channel, and you add all 3 of those together. Each one of those would be a matrix, okay, with all of its different shadings in red, green, and blue. You add all 3 of those together and you get the full color image. Okay, so a digital image itself is a matrix, and then if I add the 3 individual matrix colors together in red, green, and blue, that's like matrix addition. So here's some more matrix addition. Adding the same number to each element increases the brightness. So if I look at this picture of Neo here, and if I add, say, the number 5 to each element inside of the image, it makes every single color a little bit brighter, okay? If I take it and I subtract the same number from each one of those things, I'm going to decrease the brightness. So I'm taking each color element and I'm just subtracting the number 5 to make it less bright. So this is matrix addition and subtraction. Just adding and subtracting the same number from each element. Okay? So here's another one. I can take 2 different images and I can add them together to create a completely different image. Okay, so this is called layering. And if you have Photoshop, or if you do stuff in like with pictures and stuff, some maybe iPhone applications might do this as well. So here's just a simple example, maybe a weird one. Okay, so I have a picture of kind of a rusty metal panel. I've got a picture of myself as a pirate, and if I add those 2 pictures together, it just takes each element and adds them together. So you actually see this, both images together. And so you can see this thing that looks kind of like a spine, and it's cutting right across my little face and the teeth and stuff to make it look like a decayed image. It's just this image plus this one, matrix plus another matrix. Okay? Now, scalar multiplication also has an application. So multiplying each element in a matrix image our image matrix is going to increase or decrease the contrast of the image. So if you want to decrease the contrast or increase the contrast, well, there we go. There's the pictures. So what this means is contrast is the difference between lightness and darkness. Okay, so let's say, for example, if I had the number 5 for a pixel color, if I multiply that color by 10, it becomes 50. Now if I look at the color, maybe the color was 1, and I also multiply it by 10, now it's at 10. The difference between those two things really increased, but I multiplied by the same number. And this just increased the contrast between that image. Okay, so that is an example of matrix multiplication. Well, scalar multiplication anyway. I think I see Rowan. Hey Rowan, come on in. Okay, so what I'm going to do here is I'm going to pause for a second. I'm going to pull up a website so that you can actually see what's going on in this series of images right here. Okay, so I've taken you to a website that is showing you, well, right here in the middle is a matrix equation. And in this matrix equation, are you paying attention, little guy? Okay, you better be paying attention. You're going to have a test over this soon. Okay, so in this matrix equation, you have this variable t. T is just a scalar, and the scalar gets to change from 0 to 1. Okay, A is matrix A, and that's going to correspond to, let me scroll down a little bit here, this Lego Mona Lisa. Oh, does she look silly? No comment. And then matrix B is going to be the actual Mona Lisa. So right now, T is set to 0. When T is set to 0, if I put that into the matrix equation, 1 minus 0 is 1 times matrix A. It stays the same. And so I have all of the Mona Lisa, Lego Mona Lisa. And then 0 times B, that makes that whole thing 0. And I have none of that Mona Lisa, the actual one, Da Vinci's. And when you add those two things together, you just come up with the Lego one. I think someone's deserting us. Okay, so let me go ahead and, well, here, let me switch this now to say 1. If I switch it to 1, now those things just got reversed. So 1 minus 1 in the matrix equation gives me 0. 0 times matrix A, I get none of the Lego Mona Lisa. But 1 times B gives me all of the Da Vinci's. And now I can animate this going from 0 to 1, and you can see right here in the middle that the image is just transitioning from the Lego one to Da Vinci's and back and forth. And in here the author says that that's basically how a slideshow or like PowerPoint would work, transitioning from one image to another. He lost interest. I hope that you didn't.
Do not let your baby's bone. That's impossible. Why is that truth?
What truth?
There's